universe is calling you. The universe is calling me. It speaks both day and night. It's full of dark and light.
Hey folks, welcome to SkyTour Radio. This is Mark D'Antonio. That guy over there, that's our esteemed producer, Bill. And look, we both have our SkyTour hats on. That's fantastic. SkyTour live stream has been going gangbusters. We're doing really well out there. Hopefully we get a few more people joining us. We've got the potential. I just applied to a Harvard program to bring SkyTour much more public with education and bringing astronomy to the world. And it's going to be a lot of fun if it comes through. And with Bill joining us tonight, we're going to be talking about all kinds of things. Now, you saw in the description, it's about 3i Atlas, but I have a little secret one we're going to talk about too. Did you know that there are stars in the universe that are cannibals?
So what, do they eat other stars?
They eat other stars.
I thought
Scary
that was
sounding.
a stupid question, but it kind of makes sense.
It's exactly what they do, and here's how that works. All right, most stars in the universe are more than one. There's like we have a solitary star like ours. There's plenty of those. But many stars are binaries or trinaries or quaternary. They got all kinds of components that all have very complex orbits going around each other. And so when we see that, you can imagine that sometimes those stars might be orbiting quite closely to each other, especially if they're just a pair of two orbiting stars. Now, stars evolve. They use up all their hydrogen and they eventually become red giants. And if they're stars like the sun, they shrink down to white dwarfs. Okay, but if they're companions, the evolution might not be at the same time. They may, in fact, evolve at different rates and depends on their mass and so forth. So if you have a somewhat massive star and a smaller, less massive star, the larger star may burn through its hydrogen fuel faster, expand into a red giant, and then begin its shrinkage down to, say, white dwarf. Meanwhile, this star is going to do that later. So now you have this white dwarf sitting here, and they're orbiting closely. And then this star, say, expands into a red giant, the companion, and the white dwarf is still going around it. But something's weird about the orbits when you have stars that are this close to each other. There is something called a Roche lobe, R-O-C-H-E. The Roche lobe is defined as how the gravitational field looks when you have two stars near each other. All right. Actually, even a planet, our planet has a Roche lobe and a Roche limit. That is to say, where our gravity can be so powerful that if something gets too close to us, we can rip it apart. Okay. Well, that's the kind of thing that we're talking about here. When we talk about a Roche limit, well, stars do also have their Roche limits as well. And if we have a large red giant star and a little white dwarf orbiting kind of close to each other, as that red giant increases in size, it can fill its Roche lobe. Now, here's how the Roche lobe is defined. Think of it as a teardrop-shaped gravity well, and the point of the teardrop points toward the other star. The other star also has its own gravity well, and it has another teardrop shape pointing back toward the other star. Now, in the middle, that is where the gravitational forces are equal to each other. The big star's gravity and the little star's gravity, the white dwarf's gravity, balance. All right. But if the red giant fills that gravitational space full, it can leak through that center point onto the white dwarf over here. And that leakage can lead to a disaster, but the white dwarf at that point is cannibalizing the red giant.
Mm.
They were so nice together, for hundreds of millions of years or billions of years if they're stars like the sun. And then all of a sudden, once you become a white dwarf, you just don't play nice anymore.
But Mark, it's basically like a gravitational tug of war.
That's correct. It's always a gravitational tug of war, and it's a balance of forces at all times. So the gravity's balance between the red giant and this little tiny white dwarf over here. And as the red giant grows and fills its gravitational Roche lobe, it can leak gas onto the little white dwarf. Now, those of you that follow us in Sky Tour Lifetime, you know about something called the Chandrasekhar limit. What's that? Well, it's when a white dwarf actually acquires more mass than 1.44 times the mass of our sun. So 1.44 solar masses. And so a white dwarf usually has, well, always has less than that. But if it's in a binary system, it can acquire more gas on its surface. Now, if that number that it ended up as a white dwarf was actually small, then it could acquire enough mass so that the hydrogen gas burns off all at once, fuses all at once in what's called runaway fusion, and we get something called a nova. All right. T Corona Borealis, was one of those exact objects. It's a nova, a periodic nova. It takes about 80 years for the hydrogen gas to build up on this white dwarf surface, and then the pressure and temperature gets so high that the hydrogen undergoes runaway fusion. And for a period of a couple days, that star brightens immensely and then goes away, and the process starts all over again. Okay, that's a nova. And that still means that that's a cannibal star. It's still cannibalizing the red giant that is its companion. So when you look at the situation where the white dwarf is now just about 1.44 solar masses, and it starts cannibalizing its big star next to it, well, then the mass of that white dwarf can exceed this Chandrasekhar limit, 1.44 solar masses. And that's a magic number in astronomy and in science. And the reason it's a magic number is because at that point, the white dwarf can't hold itself up anymore. Okay. And that's because the new mass it's acquired might be more than 1.44 solar masses. And if that's the case, it overwhelms the pressure trying to hold it up. Okay. And it will collapse further. But the collapse is sudden, immediate, and catastrophic. And this becomes a supernova that you'd see in the daytime if it went off, okay, in our galaxy with a nearby star. All right. So that's typical supernova that we'll see. That's actually called a core collapse. I'm sorry, not core collapse. It's called a supernova type 1A, a Roman numeral 1 and a little a, so 1A. And that's one. The other type is a core collapse, where a massive star runs out of fusion fuel and just collapses on itself. And all that inflow of stuff rebounds off the core with the innermost stuff first, and that innermost stuff starts shooting out and now hitting into rapidly collapsing stuff outside. And it just causes the whole star to obliterate itself there as well. So that in this case, where we have a cannibal star like a white dwarf that's eating gas from a nearby big star, then as that collapse, as that hydrogen fuel goes onto the surface of that white dwarf, the collapse begins if it goes past 1.44 solar masses. And when that happens, look out, because now that white dwarf begins to collapse. It goes past the pressure that was holding it up before. Okay, and then there's a whole science there. It's called electron degeneracy pressure, but never mind. It overwhelms the ability of the white dwarf to hold itself up, and it collapses further in such a way that it's rapid and, as I said, catastrophic, and we get that supernova. So that's what could happen with a white dwarf. Okay, they can cannibalize a red giant star. Now, White dwarfs are about the size of the Earth. Okay. And that's pretty small considering that the size of just our sun, which is a relatively small star, is 865,000 miles in diameter. And we're talking about an 8,000-mile diameter white dwarf that we might get from, say, our sun. That's a lot of material compressed down into a tiny little ball. So it's very, very, very compressed. Well, uh, that's for just the white dwarf. Now, the next step is for a little more massive stars. Well, we can have two relatively massive stars. One collapses down into not a white dwarf, but a neutron star. And it's possible that the star goes supernova and the companion is not affected by it. And that little star now is just a neutron star. Those are about the size of Manhattan Island.
Wow.
You're familiar with Manhattan Island. Manhattan Island, I know you stay away from it as much as you can.
I do.
Manhattan Island is small. And if you could take a teaspoon of neutron star matter, just a teaspoon, and weigh it on the Earth. This is impossible for lots of reasons, but if you could, it'd weigh billions of tons. A little tiny teaspoon.
That's how dense.
That's how dense it is. That's right. So that's what's interesting now is when we talk about the density of these neutron stars, they're ultra dense, but they too have a limit, an upper limit on what they can handle for mass. Usually that's 2 to 3 times the solar mass of our sun, the mass of our sun. So above 2 to 3 solar masses, if you add more mass onto the surface of a neutron star, well, then it too is going to start to collapse past that ability of itself to hold itself up. All right. So the neutrons on the surface of a neutron star are packed so closely together, okay, that you can't collapse it any further because of neutron degeneracy pressure, this pressure pushing out, holding up the star. But if you add more mass over it and you go past that 2 to 3 solar mass limit, and that actually has a name, it's called the Tolman-Oppenheimer-Volkoff limit, or TOV for short. You don't have to worry, remember, it's not going to be on the test. Okay, maybe his test, but not yours. But if you get past that Tolman-Oppenheimer-Volkoff limit, what's that? Oh, is that me talking or you? I couldn't tell.
I didn't say a word. I'm listening.
Oh, okay. If you get past that TOV limit, then although you don't get a typical supernova, but what you do get is that neutron star spontaneously collapses into a black hole. Boom. And when that happens, it gives off tons of these particles we talk about from supernovae called neutrinos. Okay. At the same time, you get the massive gravitational waves from this collapse. Gravitational waves are interesting because Einstein said we may never see what they are or even understand what gravitational waves are. And then we started seeing them when we weren't supposed to ever see them. And so that showed us that we had gravitational waves. We have light waves. We have a light particle, the wave of light, or a photon, right? We have an electron, or we have a probability equation to describe where the electron is at any one point. Okay, so you can describe elementary particles and light in terms of a wave or a particle nature. That's called duality. Well, gravity is that little weirdo, okay, where we now understand gravity has waves, but where is that gravity particle? I want that graviton, right? We want that graviton. So CERN is actively looking for gravitons and these particles, actually. So there's a lot going on there. Now, in terms of the neutron stars, when they collapse and they give off all these gravitational waves when they collapse into a black hole, that is markedly different from what a white dwarf does. When a white dwarf collapses and is pushed past its limit, it's going to usually explode as in all cases, it seems, explode as a type 1a supernova again, and that obliterates the star. The neutron star, when it collapses, it becomes a black hole. So it changes from a neutron star into a black hole. So black holes have always been a really weird thing, you know? And I know that most of you know that. And where, in fact, do they come from? How does the physics work out for black holes. That's another Sky Tour radio. And maybe we'll talk about how black holes work, how they form. And as a little teaser, if you saw a friend of yours falling into a black hole, let's say we push Bill off the cliff and he falls into a black hole. He's going, he'd fall in. And then we'd see, boom, he would stop. And we'd see his image on the surface of the black hole called the event horizon. And his image would stay there for a period of time and it would slowly fade away. We'd think he got stuck. In fact, he wouldn't have. He would have just continued going on in. Okay, and I'm leaving off the really gross concept of spaghettification, stretching you out into an infinitely thin string as you fall in. That's pretty gross. Okay, but the image would remain on the event horizon for a bit of time and then it would fade away. And that's because at that point, that's the last bit of light that's slowly getting to you, still able to escape, okay, from that black hole, but not in a way that allows you to see what happened past the point when it entered the black hole, the light from his body falling in. So that's really weird. So when you look at a black hole, you could expect to see the surface, the event horizon of the black hole, littered with many of the previous things that fell into it for a period of time. Not always. And this might be a good time to talk about some of the theories of the universe.
All right, before you go there, I have a couple of questions, obviously.
Yes, you do.
What do we have on Earth, whether it's Earth-based or space-based, that can detect these processes that are maybe going on currently in our Milky Way? And if so, have you seen any evidence that this is occurring currently now? Well, before I finish that, currently, because we're always looking in the past.
That's correct.
So,
all right. So we don't even have to get caught up in that semantics. We can just say, is anything happening like that? Sure. Okay. Well, we do have X-ray observatories in space, and they're looking at these X-ray emissions that come from black holes colliding. We have we have neutrino detectors buried deep in the ground that actually detect neutrinos. Neutrinos are objects that they move at the speed of light, and they're so lightweight, so low mass, almost no mass, that they can travel right through the Earth unimpeded.
Wow.
So to trap them is kind of difficult. But in these deep mines underground, we have the ability to actually trap a few neutrinos. So when Betelgeuse, for instance, which I'm sure some of you are thinking out there, when Betelgeuse actually goes supernova eventually, and it will, believe me, it's going to, okay, Betelgeuse is going to shower us with neutrinos. And when we start to see neutrinos coming from Betelgeuse, we know to turn all our telescopes toward Betelgeuse at that point. Why is that? What do you think? Go ahead, Bill, and take a stab.
Oh, he's asking me.
Well, you are the other person, so that's in
no,
here. I mean, we have everybody in the chat too.
Why would? Because it's something that's not commonly seen.
Well, okay. It's an unfair question. I guess I didn't really phrase it too well. How will we know Betelgeuse is in the process of undergoing a supernova just because we see a burst of neutrinos from it? And the answer I'll give you, because it's really not that obvious, as it turns out, actually, is that when a star goes supernova, the first thing to come bursting out of that core of the star is this massive burst of neutrinos, way more than the star is giving out anyway, because all stars do. Where you have billions and billions of neutrinos going through you right now, right this second. Every one of you are being peppered by neutrino bullets. You don't even know it. Okay, it's constant. If you could see them, you'd probably lose your mind, because it's literally a constant sheet and three-dimensional sheet of particles going through you at all times at light speed. So that said, when you look at neutrinos that leave, say, Betelgeuse undergoing supernova, they get out of Betelgeuse first before the actual physical material shooting out from the core, bouncing out of the core, breaches the surface to signal the visual supernova.
Wow.
Okay, so you have a few hours from the time that you see the first burst of neutrinos to the time that you actually watch the surface of Betelgeuse erupt in this complete destruction. So obviously, if we lived around a massive star and we saw a burst of neutrinos come from it, if the star was very massive, like the size of Betelgeuse, we would only have a few hours to live. See, so that's, I mean, that's the universe giving you a 2-minute warning, I guess, right? But it's a little longer than maybe a 2-hour warning or whatever. But just imagine that, So, so that said, this neutrino burst is something we see from Betelgeuse, and just like with a collapsing neutron star that's been cannibalizing another companion star, we would also see that star give off as it made its way to black holedom. Okay, we would see that star give off a lot of neutrinos, X-rays. It'd be just a massive amount of radiation coming off of that region of space. So pretty interesting how that all works. All right. Yeah. So I know that that's actually really interesting. Okay. Now, as far as questions, I see questions already. He's saying, this is Wyatt Bronx asking, will it be visible to naked eye? I think you're talking about the Betelgeuse supernova. And the answer is that yes, it will. In fact, if it's daytime when it happens, right now, Orion's in the daytime sky a little bit. It's kind of coming up just before dawn. But
winter sky. Yes, winter sky. That's the time with the Orion.
Yeah, exactly. And so
would it look like a small sun or a moon? Like, what would it appear as?
Yeah, well, we see Venus as the brightest object in the night sky, other than the sun and the moon, right? And Venus is actually going to pale in brightness compared to, say, Betelgeuse. So Betelgeuse will be really, really bright in the sky. It won't look as bright as the sun. But let's suppose this happened next year while Betelgeuse was just next to the sun in our daytime sky. You'd see the sun, and if you were looking up at the sun, it's like, oh, taking in the rays. All of a sudden, you'd see this bright object appear next to the sun. And you'd say, what is that? And that would be Betelgeuse going supernova. You'd see it in the daytime sky.
How long would it appear in the sky, Mark?
It could be in the sky for a couple of months, several months, actually, depending on how long it takes for that to calm down. It is a massive star. If you put it where our sun is, it would go all the way out to the orbit of Jupiter. So the Betelgeuse is 10 astronomical units in diameter. We're 1 astronomical unit from the sun, and it takes light 8 minutes to get here. So if you do the math, you can see how long it would take actually for light to escape a destroyed core of Betelgeuse on its way here. It gives you a good idea of how long it'd be before the light reaches us, or the neutrino stream gets out of Betelgeuse to head on its way here. Now, Betelgeuse is about anywhere from 600 to 750 light years away. So as Bill alluded to earlier, when we look at Betelgeuse, we're looking back in time, aren't we? We're looking back in time almost 1,000 years, right? Yep. When you look in the belt of Orion, we're looking back about 1,500 years. We look at Betelgeuse, we're looking back about 750. Okay. So we're looking back in time at all these different points in time. So the universe is a time machine of sorts. You can look back in time. Now, if we figured out technology to have a mirror, 100 light years away, and have it turn around and look back at the Earth right now, we put a telescope on it right now, okay, 100 years from now, okay, we'd see what Earth looked like 200 years before that, because it takes 100 years for it to get here. Yeah. So we could actually see Earth, 200 years ago that way. So it's kind of cool. Or 100 years ago, right? Because then it would take another 100 years for us to see it. But it would be 200 years from our present at that point. Figure it out. You'll see. I'm not right. I'm not wrong. So yeah, pretty cool. So I'm really interested if Betelgeuse goes supernova, because
what's your best guesstimate, Mark? What do you see as the possible timetable that this could occur from any time from now to what?
Well, actually, let's be very accurate. Okay. Betelgeuse will erupt anytime between, say, 749 years ago and 10,000 years from now. Okay.
Wow.
Yeah, we don't really know.
Wow.
So Betelgeuse could already be gone if we could instantly transport right there. Betelgeuse could already be gone, and we wouldn't even know it. You know?
Wow.
Yeah, pretty cool, huh?
This.
Yeah. So I see a lot of people that I know out in the chat. It's nice to see you guys.
Yes.
Okay, yeah. Kathy Messick's with us. Kathy asked me advice about a telescope to get, and I have to give her credit. She went for it. She got herself a Celestron 9.25-inch telescope. It's literally one of the highest rated telescopes. But man, that's the one you need, because you can automate that thing. You can be in the house relaxing and watching your screen and Wi-Fi and just
You're
watch.
really going to give me that idea now to go get another telescope? Really?
Oh yeah.
You
Sure,
got,
why not?
you got two. I got plenty to watch. If I really wanted to see telescopes, I just go to your Sky 2 live stream.
Well, yeah, Sky 2 live stream is fantastic.
And what's any update before you hit the next topic? Any update on that third location possibility?
I've been talking to them, and they're excited about a third location, and this might be in Colorado, in literally one of the darkest places in the entire United States. I was there. I saw it. It's at 7,000 foot altitude. It's amazing. Looking up at the sky, it's like you can actually see the very subtle clouds in the Milky Way very, very clearly. It's like awe-inspiring. And by the way, it was on a night where there was some moisture in the air, thunderstorms coming through, and it still looked unbelievable.
Wow.
So yeah, so we're still working on it, and they initially said, well, maybe we'll think about 2028. It's like, okay, cool. And then it was, well, there's people getting excited here. They're really geeking out about it. So maybe it'll be 2026. Might move it up a little bit. So we'll see what happens.
Corner. It's right around the corner.
It is. And we have, I might as well give you the update on everything. The Sonoran scope is up and running, working fine. There was a problem. A very violent windstorm came through there recently, and it damaged the roof of not our observatory, but one of the buildings on site. And the location it damaged happened to be where our Starlink satellite dish is. So they had to take it down and put it back and fix it, and fix the roof, and then put it back on. And they did, and it works fine. So I've been using it lately to stream. I streamed 3 nights in a row. We did a Milky Way grand tour. We had part 1, part 2, and part 3. And where were you?
Actually, somebody told me, our friend James said you had an issue when we had the G3, the KP index, I think was 6.
Yeah, I had a hit from a solar flare. Even though the building was protected from them, I actually had a hit. And I got it back. In fact, it wasn't me that went out. It was Starlink.
Right.
Okay. Because our Benson site and our Sonoran site went down at the same time, because the same satellites were serving that region. So
Wow.
we lost both observatories, and I waited it out. I was talking to folks, and I said, yeah, it's a Starlink outage. It's a big spike of an outage. And I waited about 15 minutes, and it all came back. And I went back in, and there it was, still taking pictures like I had instructed it to. So we ended up with a lot more frames stacked for this one object called the Cocoon Nebula. And it was actually pretty cool. So it's actually pretty robust. I'm pretty happy with it, and I do want to remind everybody in the chat, if you have questions, please do put them in. And we're going to be talking about a lot of these things. So if you got any questions, just put them in, and I'll be happy to talk to you. Like one thing here is Benno says this. Benno from Australia. What is the larger comet coming now? The backyard professor mentioned it. Yeah, this is there's a comet Swan that's out there, and later in October it's going to be in some prime viewing position, and we will look at it from both Benson and from the Sonoran, and it's going to be really pretty. and we will be imaging that. So I think that's pretty good, you know. But yeah, and I'll give you more details on that, you know. Yeah. So anyway, I'm really happy that you guys are here tonight, and like I said, Bill's with us, our esteemed producer. Couldn't do this without him. And you know what? I gotta blame him for something else.
I miss Tara.
Yeah, Tara. I asked Tara way too late to join us tonight, and it's my own fault. She didn't even get the message. So, you know, knowing Tara, she's gonna feel bad, and it's my fault. I got caught up trying to get the Benson security camera that was literally sheared off by the roof when it went haywire a couple weeks ago. That's fixed, by the way. I tested it a little while ago. The new camera's installed thanks to Glenn, who lives in Benson, and he helps do some maintenance for us all the time. He's really fantastic. And excuse me. So when that got sheared off, I was just like, oh. So I was trying to work through getting him to put this bracket on that I sent him and all that. He bent it to the right angles and everything and put it up in the building. And it completely escaped me that I had a show tonight. So I admit when I'm wrong, and this is one of those times.
There you go.
You know. So, hey, you know, it's true. But yeah, Michael Hedrick, yeah, click that like button.
I will say with everything, because with my position on the station,
yeah,
and so much talk about 3i Atlas, it's refreshing to hear the science coming from a person of your position to fill us in on the facts. Because there's so much talk out there, Mark. I mean, it can make your head spin, and I'm thinking of a movie.
Mm-hmm. Look what Sam's saying.
Oh, look at perfect timing. Thank you. Thank you for putting that in there.
Yeah. Thanks, Sam. Very well done. Very well spoken.
Perfect
yeah.
timing.
And yeah, the problem is that when 3i Atlas was first seen, I thought, oh, it might be like 2i Borisov, which is a comet that came through. Or maybe it'll be like 1i Oumuamua. We've seen three interstellar objects coming through. Now, it's important to understand why we know they're interstellar. How do we possibly know when you see a little dot moving through the sky? How can you know that's interstellar? Come on. Well, actually, from science, what we can do, we're using calculations for the trajectory and the orbit of these objects by multiple observations. And I went through this when I was getting my degree in astronomy. We did calculate orbits of objects. It is slow and methodical, and when you get it right, it's accurate to a very, very small percentage. So the orbit calculation for this object shows that it's no danger to us. It's going to be well over 100 and something million miles from us at closest approach. But how do we know it's how do we know it's interstellar? Well, first let's look at the anatomy of our solar system. We have the 9 planets. They're in a plane. Okay, they're all orbiting the sun. The sun's in the middle, and they're all orbiting the sun. Okay, in a parallel line. Okay, and as seen on the edge. And then Pluto's a little higher and orbits sort of at a odd angle, but it's still a planet as far as I'm concerned. Yes, that's right. All right, and outside that, we have a belt of icy objects and another horizontal circular belt. If you look down at the top of our solar system, it's a circular belt of icy objects. That's called the Kuiper belt, and that's spelled Kuiper. Beyond that, there's an Oort belt, Oort, and there's a belt like this. It's a circular belt beyond the Kuiper belt. Additionally, there's a cloud, a 3-dimensional spherical cloud of objects around our solar system called the Oort cloud. That's so big, right, that it extends more than halfway to Alpha Centauri. It's a huge cloud. This is information we just kind of had theorized, but now we're kind of showing. Well, anyway, the Oort cloud, if you disturb an object out there, let's say from that kind of distance over millions of years, a star may pass by and tug on one of those objects out there and start it on that long millions of year journey into our inner solar system. Well, if it does that, the speed it can reach is only a certain maximum speed. It can't go any faster than a certain maximum speed, falling in from the farthest reaches of that Oort cloud. When we see these objects come in, all right, and they're out like at Jupiter, so they're kind of in the outer solar system right now, and they're going 137,000 miles an hour. We know that they came in with a very high velocity. They plunged through the Oort cloud because it would have to have come from much further beyond the Oort cloud to pick up that kind of speed. And that's what we see. So the speed tells us. Now, the direction also helps us a little bit, but it's usually the speed which tells us that these things came from such a long way away. Okay. Now, that said, this object, like one eye, the eye means interstellar, and one means the first one. One eye, Oumuamua, came through. They erroneously said it looked like a spindle that was like 700 feet long and 70 feet in diameter. That was totally wrong. That's not at all what it looked like. It looked like a pancake. Okay, they were correct about the cross-sectional width, but not about the actual diameter. Its diameter was way larger. So it was tumbling through our solar system. And as it came through, when this side was facing the sun's radiation is hitting it, making it move faster than when this side was facing it. So it would move erratically a little bit as it moved through our solar system and on its way out. And maybe that's why it changed its course and speed as it left. However, as Avi Loeb, who I know, okay, has said, we can't deny the possibility that maybe it was, some kind of interstellar probe from an advanced civilization. Why would we say such a thing? At first blush, you might say, oh, that sounds kind of crazy. Why would you say that? Well, there's actually good science behind it. If we look at the objects coming through our solar system, we look at these objects and say, okay, well, we know that's a comet. We know that's an asteroid. But here comes this thing, and it comes in from a high location and comes zipping through and then leaves really fast. When we look for things that go through the solar system like that, it harkens back to a point in time when we ourselves said, hey, let's create something called a solar sail, which will actually use the pressure of the sun's radiation to propel a ship out of our solar system and maybe get it into another solar system where it could use that particular star's solar radiation to allow it to fall in with gravity and go out with gravity, the solar stellar wind pressure from that star. So it wasn't far-fetched to think that maybe another civilization thought of using a solar sail as well, or a stellar sail. Okay, a very, very large object. And so when Avi suggested that, he suggested it because the object wasn't a spindle, it was a large pancake. And that's what a sail would look like to us, a large pancake. So that wasn't far-fetched at all. All he said was, we can't deny the possibility that this could be that. And he's right. He's absolutely right. We cannot deny that. And I'm okay with that. I think that that's correct. And I'm not saying it just because I know him. I'm saying that because he's right. As a scientist, I see it. Other people see it. Now, with this object, he's saying again, similarly, that this object is doing odd things. And he's not wrong, once again. Now, I will say that in this particular case, 3I/Atlas, Atlas, by the way, is the name of the telescope that found it. It doesn't have an actual name yet. So 3I, whatever it's going to be, currently Atlas, it's moving at that speed of 137,000 miles an hour. And as it comes through the solar system, it's going to do something interesting. It's coming in actually along the plane of our solar system. So if the planets are all going around the sun this way, it's coming in right along the plane of our solar system. And it's actually going to pass Jupiter, it's going to pass Mars, and it's going to pass Venus on its way out. Okay? So there you see this image of it, right? And so what's interesting about this is that this particular object, if it was just a random piece of ice or a comet coming through, it would seem very odd that this is actually coming through like that. In fact, the statistical probability, okay, of it doing that are very slim, less than 1/10%.
Wow.
That's actually a very, very small percentage. So that's one oddity. The other oddity is that this object, and this was an image of it taken by the Gemini telescope on Mauna Kea. Another oddity is that it seems to be emanating a lot of carbon dioxide. So in that fuzzy picture you see there, you notice how there's like an extended envelope of stuff around the core. Well, the core we can't even see, right? When we think about the core of this object can be anywhere from 1/4 mile in diameter to 25 miles in diameter. Okay. We don't know because this stuff, right, is actually causing a problem. This stuff allows us to, or effectively blocks what's inside. But what we noticed about this is it's giving off a ton of carbon dioxide. I don't mean just a ton, it's giving off a lot of carbon dioxide. In fact, the bulk of the stuff that we saw in here, when you look at the spectrum, we're looking at dust right here, okay? But when we look at the spectrum of the gas that's in this envelope around this comet thing or whatever it is, we're talking about mostly carbon dioxide. Now, comets generally have some carbon dioxide, maybe 3 to 4%. They have cyanogen, which is a carbon atom with a nitrogen atom attached. That's called cyanide. We don't want that. Okay. And they have methane ices. They have carbon dioxide ice. They have water ice. And you see other, you can have some actually rather complex hydrocarbons, things called tholins on the surface of these comets. And these are all the building blocks of life, basically. So we're noticing that this comet more and more, or this object, okay, more and more is showing that we're probably looking at an object that's now looking more and more and more like a regular comet. But there's still differences. All that CO2 coming out of it is odd. We don't expect that, as I said. Another thing we're seeing coming off of this that we didn't expect is nickel atoms. Nickel, it's in the periodic table, right? So when we look at nickel atoms, nickel is a very if we look here, okay, you look here and you look at number 28 in the periodic table there, you have iron number 26, you have cobalt, and then you have nickel number 28. Okay, well, nickel is something that is produced when massive stars explode or when white dwarfs explode. So obviously this came from a region that was really heavy with exploded star debris, perhaps. Okay. And that's kind of interesting too. And the problem is, again, look to the left of nickel by 2, and we go to 26. That is iron, Fe.
Mm-hmm.
Well, iron would also be expected to be visible at this point in this comet. If we're seeing nickel at 28, we should see iron, and we don't. It's not right to see iron or nickel without iron, because iron and nickel, the processes in the universe that create each are kind of intertwined with each other. So that's kind of weird. So the nickel atoms are strange, and that's something that has yet to be explained. So all that said, we have some serious issues with how the composition of this thing came to be. Now, again, it came in on the plane of our solar system. What does that mean? It means it came from the galactic disk. When we look at our galaxy, it means that this came from our galactic disk. And our galactic disk is something that has dark nebulae in it. It has star-forming regions. It has spiral arms. Okay, that's where our galactic disk is. Okay, so in this galaxy that we took, you can see the spiral arms. Okay, actually those red little bars there, the horizontal one and the vertical one, this is a supernova in a distant galaxy, incidentally, that we took a picture of. All right, it was supernova 2023 IXF. For those that want to know, this is also the galaxy Measure 101, M101. So, but you see the spiral arms, and it's in these spiral arms and that disk of the galaxy where we think that this object formed. Now, I have a theory as to why we see so much carbon dioxide, and this may bear fruit if we can look at it again with the James Webb and with the Gemini telescope as it gets closer. And that is that maybe this object was born in a region that was high in carbon dioxide gas as a molecule, and then it accreted onto this comet's surface as carbon dioxide ice, dry ice, CO2 ice.
Would that explain what people say is a less visible tail of the comet because it's composed of that instead of, say, water ice?
Yes.
Because that's what it doesn't have a tail like a normal comet. That's because of its composition.
Well, yeah, but we also have to understand that it's just kind of inside the orbit of Jupiter at the moment, getting a little closer. So it wouldn't have much of a tail anyway at this point, but it does actually have a tail right now that's been visibly spotted. And right now it's in the constellation Libra, and I can't use the Sonoran telescope to look at it because the Sonoran telescope's a wide field system. But our Benson telescope is perfect to look at it, but it's cloudy in Benson right now, or I'll be doing this right after this show. We'd be all going looking at 3i Atlas, okay, before it sets, because it's in Libra, and Libra is going to be setting about an hour or so after sunset, and it's already about 15 degrees above the horizon, so it's already very low on the horizon.
From your location, what date would be best to view this if you had a choice? Is it in October, like December? Because I'm hearing all kinds of different dates.
Yeah.
To this.
Well, October, I believe, is the closest approach to Earth, and then December is closest approach to the Sun. Okay, but you can verify that by looking that up. But the point is that when we talk about this object, we have to understand that first of all, it's no threat to us. We also have to understand there's a few characteristics we want to learn about this thing. We don't know why it has all that nickel that I mentioned. We don't know why it has all the carbon dioxide. Why are we seeing nickel spectra with it? That's weird. We don't know. That's a strange one. But then again, it's only the second interstellar comet we've ever seen, if it's a comet, right? So the first was Borisov, which was 2I Borisov. Okay, so and you know, to Sam S's question way earlier, when we talk about this object, we have to understand that there's a lot of crap that's put out there, a lot of really bad, awful, wrong stuff. It's put out there just so people get clicks on their videos or whatever. You all remember Star Trek, I'm Captain James Tiberius Kirk. Remember? Captain Kirk. Well, Star Trek, the original series, there was an episode called The Doomsday Machine, and it had a planet killer, and it was a conical shaped thing, and it looked like the devil himself, according to Chris Decker, the captain of a spaceship that transported all his people down to a planet that the planet killer then destroyed, and it made him go crazy. Okay, it was actually a very good episode. Well, the planet killer itself was a long conical thing. It was hollow, and you could look down. It looked like one of those, like, remember those snacks called Bugles?
Yes. Yeah.
That was what the planet killer looked like. It looked like a bugle. Well, anyway, a snack called a bugle. Well, anyway, I saw lots of people online showing pictures of that thing snipped off an episode of Star Trek and saying, latest image of 3i Atlas.
Oh, my.
Oh,
Oh, boy.
and that's why I wrote that long post. If you look on my Facebook wall and scroll down a little bit, you'll actually see my article on 3i Atlas, and you can see, for all to see, what we know about it, what it is, and I don't take away the possibility that it could be some kind of interstellar probe. I don't, because we certainly don't know, and it would be arrogant to say it's not an interstellar probe.
Right. Definitively, yeah.
Yeah, you can't do that because how do we know? You know, and I get that. I get that. So, yeah, okay. And that's. Let me get this back up here. Was this correct? Perihelion, that is closest to the sun, will be on October 29th. And will pass about 1.8 astronomical units away in mid, and I'm going to say December, right? You're supposed to say?
Probably, yes.
Yeah. And thanks, Wyatt, for putting that up, because I wondered, I couldn't remember which date was the perihelion date, but that would make sense. Yeah, because it's going to come by, it should come by us first, I thought. Well, anyway, we'll get that correct. And so bottom line is that we're going to end up seeing, by October 29th, it's going to be closest to us, or it's close to the sun, rather, us being the solar system. And it's going to be between Earth and Mars. Again, that's Wyatt Bronx adding this for us, helping us out. Thank you. And so all good. So, and it's going to go on its way out. Now, the reason it's not going to stick around is because of the fact that its orbit is something called a hyperbolic orbit. Now, we have circular orbits, like the Earth going around the sun is almost, not quite circular. It's a little bit elliptical. Okay, same thing with the moon. But we also have elliptical orbits. Now, elliptical orbits are more like, an ellipse, right? But then if you can imagine, if you go even faster, then you can't, when you're going around the corner to get to that next, to orbit this circle, you might be going too fast. So we end up going like this. Okay, so you might get like something called a parabolic orbit. And then beyond that, you get something called a hyperbolic orbit, where it's going way fast. And it comes through so quickly that it just curves a little bit due to the sun's gravity and then continues on out. Boom, and away it goes. And that's what this one's going to do, right? It's already moving fast enough to escape the sun.
All right, there is a couple of questions before we go to break.
Yeah,
Michael, I'm going to put it on the screen. Michael asks, has Atlas made any non-gravitationally influenced changes in speed or direction?
Not as far as I've seen. I mean, first of all, comets alter their own courses by how much gas they eject, and it's called outgassing. As the sun heats the surface of a long, dormant, cold comet surface, there's gas trapped under the surface of the comet, and that gas can escape like a rapid jet, and that acts like a rocket exhaust, and it can propel the object, the comet, into a new, not like necessarily a new direction, but it can actually propel it in a curved path that might be a little bit different from where it was traveling before. So we might see that happen.
Here's another one from Donald before we get to the break, so we got like 3 minutes.
Yeah.
Did you discuss what if 3i Atlas uses Mars or Jupiter to turn, and any kind of a slingshot effect, I'm assuming?
It's actually going to do that. It's actually going to, in fact, let me bring up that image again just to show you. You can actually watch that. You don't really see it, but it's curving around Jupiter a little bit, and then it's kind of curving, but the sun is assisting here, all right? And the passage to Mars is probably keeping it from curving too much toward the Earth, all right? But it's going to continue on out. Now, what's not shown here is Venus. Venus is also going to be passed by this as it goes by. Venus is a dot to the right of the sun there, but it's gonna Venus's orbit's going to be in such or the planet will be in such a location in its orbit that it will end up passing relatively close to Venus on the way through. I don't mean like within earshot of it, right? No, it's going to be millions and millions and millions of miles away. Okay, but the reason why it makes so much sense to think that this might have been a probe is because that as this thing is coming through, it's hitting some of the most important planets in our solar system, going by them. And if you were launching a probe to another solar system and you knew what planets were there, you would probably choose these planets. Now, people say, but why not Earth? Exactly. Why not Earth? I think I look at it like this. Why don't we just let the Juno probe around Jupiter? And bear with me. Why not let the Juno probe around Jupiter just keep orbiting Jupiter? Eventually, the orbit will change and it could end up striking one of the moons or whatever. Is that such a big deal? We think so. We don't want to interrupt any potential evolution on Europa if there's life there. So we are going to crash Juno into Jupiter's atmosphere, right? And make it so that the probe can't ever collide with another moon and contaminate the surface of a pristine moon. So if we have an alien race that is a few light years away and they send a probe to our solar system, they know that there's a planet here that's blue, has oxygen, is probably Earth-like, populated. Why would they want to potentially contaminate it? They might take a long, wide berth around it just in case. And they're passing Jupiter, they're passing Mars, and they're passing Venus. But they're not going to pass Earth. That omission is even more important to me than if they did pass Earth.
When we come back from the break, I'd like you to answer this question for me. With the current equipment that's on Juno, is that the best equipment that we have at our disposal to get any kind of scientific data? I think it's mid-March. Well, not actually, because they were going to plan on sending it on a mission to get as close as possible. I don't think that happened. So when it makes its approach around near Jupiter, is this the best scientific equipment that we have at our disposal to get the analysis that we may need from Atlas? Or is there something that we have that can provide more information than what Juno could?
I think that my camera's frozen. Sorry. I think that that's true. We might actually be able to get more information using Juno. I know that Avi suggested using that, but I don't think they're going to do it.
They're not.
I don't think so. I wish they would have, but I don't think they can.
All right. Well, we'll go to break and we'll be back and continue this conversation. So stand by, everybody, and we'll be right back in a few minutes.
Hey.
To your seats, Cosmic Explorers. KGRA Digital Broadcasting, the unrivaled #1 source for raw, uncensored paranormal and UFO talk radio, has just unleashed a sizzling online merch store. Stay cosmic on the move with accessories, rugged phone cases, vibrant yoga mats, and notebooks perfect for jotting down UFO sightings. Ignite your obsession with the unexplained through bold, exclusive gear that demands attention. Kicking off with the Supernova, the store launches 2 heart-pounding collections, KGRA Digital Broadcasting and Bishop James Long. Every item you grab helps power the network and its groundbreaking shows. Stand with the truth seekers, act fast, score your stellar swag, and join the uprising today.
As UFO reports come in from around the world, the Mutual UFO Network, MUFON, is there. We continue to explore new cases and build our massive database. We share our information with the world in a number of ways. If you would like to be part of our investigative team, you are always welcome. What could be more exciting than exploring the UFO question firsthand? Join MUFON, find your friends.
And welcome back. And it is I back again here. I think I marked Antonio. Am I correct?
I hope so. Am
I
looking
think so.
the right way?
Yeah. I think I am. Yeah, sorry about my camera froze there for a moment. I had to get a different camera server running. So anyway, we were talking about this 3i Atlas, and the thing that's the most fascinating to me about 3i Atlas is that it's turning what we understand about interstellar objects on its head. Now, granted, we have theories, ideas, thoughts, and based on our understanding of how the universe evolved and where it came from and how it came to be, it seems like we should have a good handle on it, right?
But we're new at this. Is something that we're still getting familiar with. That's the thing. We this is the third one. We don't have much to go on with these interstellar objects, so it's a learning curve. Pretty much,
it is a massive learning curve for us right now, and I know that it's going to be very difficult for us to coalesce what we're seeing with this guy and say compare it to Borisov. It's like, I don't know,
I want to share something with you and the audience, because this is a letter that Anna Paulina Luna sent out to the acting administrator for NASA.
Right. She wanted to have Juno redirected.
Yes. Yeah. And here it even says that if it didn't have the fuel, if they couldn't do it, it's still going to be of great value. If insufficient fuel is left, if they don't have it, then it is from its current orbit of Juno, it'll still be of great value.
Yeah.
So that's
her letter. Yep. That's the letter. And see, my feeling is that when you look at members of Congress now calling for this type of action, that's really interesting. So on one hand, they're taking funds away from NASA. On the other hand, they're encouraging NASA to do other research, so that's all good. And but as far as I know, NASA's not choosing to do this.
It's done because they were supposed to do it by, I think, September 14th.
Yeah. I mean, they could still point Juno at it and get photos.
Exactly.
But I think they've chosen not to do it. So I'm not happy about that.
Neither am I, because if they're going to just deorbit it and burn it into the atmosphere of Jupiter, they could have done this at least made the effort, try.
Yeah, I know.
For science. And it would have cost, there is an amount here that you mentioned that there was a budget amount. I think it was $15 million over 6 months to extend the mission. So there was a budget involved here with this, but I guess it's not going to happen like you said.
Yeah, and that's, you know what? We're going to have the Gemini telescopes on Mauna Kea. We're going to have James Webb.
Yeah.
We're going to have Hubble. We're going to have the ability to see this in similar ways that Juno could have showed us.
Well,
But Juno's cameras are unprecedented in their quality, and the resolution is really quite good for what it does. And I thought maybe that'd be a perfect idea, but no. I'm not an NASA administrator. Yes, I am saying I'm trying to hide a lot of what I'm thinking. Anyway,
I got a silly question for you.
oh, you know what? You're always full of silly questions.
Right? Is this giving off any specific color? The comet, because that's what I'm hearing a lot. A lot of people saying, "Oh, it's green, it's this, it's that." Would that be similar to, say, a meteor burning up in the atmosphere and giving up its makeup by its color? It's
A little different. First of all, let's talk about what the comet is made of. We talked about the carbon dioxide. There's a lot of it. There's also carbon monoxide, which is a carbon atom and one oxygen atom. Okay. Remember, carbon dioxide is carbon atom with two oxygen atoms. Then we have carbonyl sulfide, which is a carbon atom, an oxygen atom, and instead of another oxygen atom, which would make it CO2, it's a sulfur atom, making it COS. All right, so carbonyl sulfide is the other thing we're seeing. Again, not uncommon in comets, actually. We also are seeing the cyanide, as I mentioned, cyanogen, CN, carbon atom with a nitrogen atom. And that is known to show green, as is carbon. Okay. The spectra of a carbon will show in the green. The spectrum of carbon or cyanogen will also be green, and the visual spectrum. So it gives off these lines in the green line of the spectrum, which shows us the green color. And sure enough, 3I Atlas is looking green now.
right.
So we know that it's made up of similar chemistry as other comets, at least to this point, but it looks a little different. It's acting a little differently. Why the carbon dioxide? Why the nickel atoms? That's really weird. Okay, so that's that. Now the question then becomes, well, what about its age? How old is this thing? Well, it came from outside the solar system, and that means that based on the location it's coming from and going back in history to where we think it could have come from, which we don't actually even really know quite yet, this object looks like it could be up to 7 billion years old. Now,
Mark, would I don't mean to interrupt you, because I always do.
Yeah, you do.
Is this coming from our own Milky Way? I mean, is it coming within our own galaxy, this object? Yes,
it's coming from the interstellar space around our solar system within our galaxy. So it is from outside our solar system. Okay, we have our solar system, right? And we then have our solar neighborhood, the stars near the solar system, okay, and the sun. And it's probably maybe from one of those stars. But those are all light years away from us. Right. So it means it will have been traveling billions of years in order to get here. Okay, and that's the important thing to keep in mind. So that said, as it's made its way in through the interstellar space in between stars, the gravitational pull of the sun managed to pull it in, and now it's making a one-time trip through the solar system. And it's coming through at a very high rate of speed, as we know it should, because it's interstellar. Now, if it's 7 billion years old, you got to keep in mind that that's almost twice the age of our solar system. That means, that's tantamount proof, in fact, for those that don't believe there's planets elsewhere. That's tantamount. That's actual proof, definitive, hands-on proof that we have objects older than our solar system out there that come from other stellar systems, and this is one of them. Now, as I said, its speed is about 137,000 miles per hour. That's actually pretty fast.
But if you did the math, the equation of math, what is the speed of light? Because if we're talking light years, if we did the math, it's traveling at 37,000 miles per hour, and it's been traveling for billions of years. Would that equation tell us roughly how many light years, when you do that math, how much it may have traveled? What's the nearest system from that direction that it may have come from to try to figure out its origin?
Well, the nearest system is 25 trillion miles, 24.5 trillion miles away, and that's the Alpha Centauri system, 4 light years away. And a light particle, light photon, travels 6 trillion miles in a year. So if you do that math, you add it up and figure out if it was, we don't know how long it's been traveling in interstellar space. We don't really precisely know its age, but we do know that the object is, very, very old, and when it gets closer, we're going to have confirmation of that age, because we'll be able to look at what's coming off the surface and be able to figure out what isotopes we're looking at. And knowing the composition of typical comets, we'll be able to figure out, based on the isotopes we're looking at, that is, the different types of a single type of atom. Like carbon can be a carbon atom, or it can be carbon-12, where there's more neutrons in the nucleus. Carbon-14. Okay, there's, again, the number of neutrons changes depending on age, right? And so that can affect what we come up with an age for this object. And that's very important too. And that's something that right now it's just sort of a guess, Yeah. So that's interesting. And it's going to get about 170 million miles from us, I mentioned earlier. And that's just shy of the distance to Mars, right? So we're talking about an object that's going to come somewhat close, but not very close to us at all, So it's actually going to be a very quick Speedy Gonzalez that goes through our solar system.
Is there any way, if this was detected earlier, that we could send some type of probe, slingshot it, to maybe get a closer view? Not now, obviously, it's too late for that now. But in the future, is that even a possibility, to try to get as close as possible, or even land a probe like we see with asteroids to get actual data, samples, analysis from the object? Is that even possible when it's moving at 137,000?
Well, I mean, as long as we can match the speed and use gravitational whipping to kind of propel us up to the right speed, and sure, there might be a way. Don't forget, we landed on the asteroid Bennu.
Exactly.
Okay, and we dropped down, bounced, and picked up stuff to send back to Earth. And don't forget, we also landed on a comet already. We landed on an asteroid, Eros. In fact, a good friend of mine was on the team that landed on Eros.
Was that the ESA? Was that the European Space Agency that did that? Or what agency did that?
Goddard Space Flight Center. It was called the Near Earth Asteroid Rendezvous. Okay. And a very good friend of mine, an astrophysicist actually, was on that. She's passed away, but Sister Mary Ellen, she was a Catholic nun.
Wow.
I'll tell you a little quick story. She was here just visiting, and she's a little white-haired old lady, and I stereotyped her as being a little white-haired old lady nun, probably doesn't know much of anything about astronomy, right? So she started talking about the pictures that the Hubble Space Telescope takes. And I said, oh, yeah, the Hubble's great. I said, I've got some nice pictures. Would you like me to print them out for you? Oh, I'd love it. So I printed out some color pictures of these things. And she was here with her friend, Florence, all right, who is a cousin, actually, which is why she was there. And I'm sitting down with her, and I'm explaining how these pillars of creation were formed, and the dark nebulae and all that stuff. And she's nodding and nodding, and Florence is starting to laugh. I'm going, and it's getting actually rather annoying, and she's sort of being rude. But how do you tell another nun she's being rude, right? I don't want to score points with the big guy, right? That's what they call him. So I finally slapped the table and I said, Florence, What's the deal? And she looks and she starts laughing. I could see she was laughing so hard. She was stifling tears of laughter. And she points at Sister Mary Ellen, the nondescript little white-haired nun, and says, she's an astrophysicist.
Wow.
Really? I know your work. It was amazing. So that was really funny. And I didn't, and I said, I'm not worthy. And she laughed it off. I gave her the pictures. But she goes, but I do, I was actually focused on chemistry. So, I mean, from a chemical perspective, tell me about these things. And that I could speak to. And so we had a very nice discussion about the chemical properties of nebulae and things like that. And it's just hard. You think Catholic nun, so you never thought that there was that kind of intelligence. I hate to say it that way, in the Catholic community, where they actually had people that were astrophysicists that were in the nunneries. I don't know what you call those. Okay, in the cloth, but apparently it's true, and I was humbled very much by that. It was incredible. So that said, I mean, we had a lot of other surprises too. With a lot of the astronomical discoveries. But when this guy comes through our solar system, we're going to end up seeing, I think, some new stuff we haven't seen from comets before. Because what are those nickel atoms doing? What are they doing emanating from this object? They shouldn't be coming off this object like this. Okay. I mean, yes, they're tied up in the dry ice that's on the surface. That's my guess. And they're being propelled off by the little jets of trapped gas as it heats up and goes, psh, psh, psh. And that it causes it to come off the comet and go up into the area around the comet, and that's called the coma. What we say is a coma, and that coma of the comet, all right, is composed of these atoms with carbon dioxide and cyanogen and carbon monoxide and water ice and carbon dioxide ice as well. So we're going to see a lot of different potential elements and compounds in this cometary atmosphere, so to speak.
All the focus will be on this. That's for sure.
Yeah,
I would assume.
that's right. That's right. That's funny, Genghis. Sounds like a show. Welcome to None of the Nebulas.
I don't know. Laura mentioned this. I'm just going to bring it up. She says that 7 new comets just entered our system.
I have a number of new ones. There's a comet Swift, which we're going to look at into October. This one here, we may or may not get another view of it. I'm hoping we will. And there's a few others that, yes, are here. A number of them are also named Atlas, because Atlas, again, is the planetesimal study telescope that's found them. Okay.
Where is that located? Where is this?
There's several observatories that have Atlas telescopes, I believe. And so
really?
They're scattered around, yeah.
Okay.
Because they're trying to do a survey to make sure that we're safe from impacts and stuff.
Is that more for the NEO?
Well, they'd be considered NEOs, right? So it searches for NEOs, near Earth objects. And so the comet is initially going to be put on when it's first found, an object's first found, it goes on a list. That's called a sentry list. Okay, like sentry guard, right? And the sentry list is for potential dangerous objects. And the sentry list will then be used to categorize these objects that are near us that may be of danger. And then they refine the orbits of these things. And only after they refine the orbit to the point where they know, without a shadow of a doubt, that it's not going to hit us, do they actually take it off the sentry list. Yeah. So it's pretty interesting. So I think it's fascinating. Now, this. So that's what we kind of know about 3i Atlas. No baloney, no sensationalism.
All right. We won't really know more until, I'm sure, like you said, James Webb, Hubble, etc.
Yeah.
But is it really that date, October 29th, that we're going to definitely know more about it?
No, I think up to that point, it's getting closer and closer. Okay. But we also have to keep in mind, and I don't remember where the trajectory is going to take it, but it's going to end up going into the not into the sun, but going to be in a daytime sky for some period of time, I believe. And only after it comes out of that will we actually be able to see it again. Obviously with a telescope. Now, if you can figure out a way to subtract the emitting molecules of oxygen and nitrogen in our atmosphere that makes the sky blue, and pierce that so you can see the daytime sky stars, you'll be a multi-trillionaire. There you go, chat.
That daylight.
Yeah, just subtract daylight from your images. Yeah. I mean, the starlight's still coming through. It's just a matter of isolating it from the oxygen and nitrogen. You know, that doesn't sound like it's too hard. You should have to work out a way to do that.
I was going to say, if anybody would figure out a solution, it would probably be you.
Well, I'm just thinking that's a specific that's a specific set of frequencies, and if the starlight are those specific set of frequencies, that's a problem. But we should be able to. Certain objects would be able to show. I would do a test with Betelgeuse and Antares probably, because they're big and orange.
He's thinking about it now.
I gotta stop thinking about it because it really comes down to having some kind of a dynamic filter that you can take away. Oh, I know someone I can talk to about this actually. I'll talk to my friend. I'll talk to a friend of mine.
Get on it, because that would be just right now with everything going on. That would be a major breakthrough for now, future.
I imagine so. Huh? That'd be pretty cool.
Oh yeah.
Yeah.
Is there any closing thoughts on Atlas? If anybody's got any questions in the chat, please post them and we'll get them asked to Mark. What would happen if it did hit the sun? Just out of
well, the sun would be dislodged. It would rotate over, probably explode. I'm just kidding.
It would just be consumed.
Nothing would happen.
Nothing. Yeah.
Yeah. Remember, this thing is anywhere from quarter mile across to maybe say 28 miles across the nucleus, and the nucleus is going to be kind of a rocky center, kind of like the Tootsie Roll center of a Tootsie Roll Pop.
Speaking of an impact, let's not forget it was during the lunar eclipse. And Mark was doing a live stream, and
that's right.
He caught a meteor hitting the lunar surface.
That's right. Right in the middle of a lunar eclipse.
Less than a handful of people caught that. He was one of them.
That's right. Around the world.
That's
right. That's right. And we were one of 5 people that actually caught it, which I thought was pretty cool. Which I thought was really cool. Oh, hey, thanks, C&D.
Yeah, that's true too. It probably wouldn't even make it it would burn up. It wouldn't even make it to the surface of the sun.
No, the sun's surface is 10,000 degrees. So, so this is a good question too from Fungway Reldman. That means Wrong Way Feldman, by the way. If you remember Gilligan's Island, Wrong Way Feldman. What? I think I can go this way. I think that wasn't it Gilligan's Island, Wrong Way Feldman.
It was, I think.
All right, he writes, maybe I missed it. Why the tail is not pointing in the expected direction? Thanks. That is a question that I don't really know the answer to, and I'll tell you why. I don't have enough data on the comet thing to know whether we're just seeing the dust tail behind it, but as it moves toward the sun, the tail might be to the left of it, and it looks like it's moving into its own tail. So maybe it's not actually in front of it. Maybe it's actually behind it, but it's a perspective illusion. That's just a suggestion. I don't know yet.
There's actually a really interesting question as well. I'm going to put it up on the screen. This is curious. If there's some kind of an ejection coming from the sun, a CME, could that change the trajectory?
Well, you have to keep in mind that the things that influence the trajectory are the object's speed, too. The slower it goes, the more gravity of the sun will affect it. But it's moving quite fast. So a CME could impact it, and if it impacted it, it could cause it to actually give off quite a show. I mean, it could cause it to uh, uh, spew lots more particles, making it highly visible. Um, and the only thing that might see it is the SOHO observatory that's orbiting the sun.
Mm-hmm.
Um, so, but that is a very good question. I think that the CME wouldn't really change its direction very much. They are physical particles, so there would be an effect, but it probably wouldn't be an effect that's major, if you know what I mean. So maybe not, So I think that's pretty cool. No, that's a good question, though.
That is.
Yeah. So one thing I also want to bring up with you guys is that um, I'm going to be heading out there again, I think, next month, because we're going to be possibly changing our Sonoran telescope to the new system, meaning instead of a large, giant computer that's running the telescope, we're going to change to a little mini computer, and then we're going to change the mount. So and raise the mount higher in the room in the building, so that when the roof comes off, we'll be able to look over the top of the roof and see closer to the horizon. Now, that's in astronomy. We never look at anything that's near the horizon because the too much air and too much atmosphere, and the views are terrible. But for outreach astronomy, which is what we do, it might actually be pretty nice. It might be pretty cool to see it. So we'll see. But I'm thinking about doing that when I go out there next month.
I am looking for a specific PDF. It has to do with this buzz going around about evidence of life on Mars.
Oh yeah,
You want to in a little bit on that?
Yeah, I actually I was wondering about that because I saw something on this just recently, and I was curious if maybe there was something like it was a Jezero crater where Perseverance rover was rolling around.
I got the PDF. I'm going to look for it while you continue. I'll see if I can find it.
And it was looking the Perseverance rover has been collecting rock samples with one of the express missions of the Perseverance rover, and that is to look for indications of past or present life. And there was a rock called Chiyava Falls, I believe, and it's sort of a mudstone, so it was made with water, and it contains a unique texture and a mineral composition, and it also has something that they're calling leopard spots. And these leopard spots are an interesting characteristic because they're rich in a iron phosphate compound. You might say, well, who cares? What's that? All right. Well, they're also rich in this iron sulfide compound too. And now the thing about it is that on Earth, these minerals are often formed in oxygen poor, water rich environments where microbes perform the chemical reactions to generate energy. So this is something that means we might actually have found evidence for life in the billions of year old waters that used to flow in Jezero crater.
Yep.
And I think that's pretty cool.
That is awesome.
Yeah. And incidentally, on the South Pole of Mars, I think it's a kilometer down, they used this ground penetrating radar from orbit, and they discovered a briny reservoir of liquid water under the surface. Now, the pressure on the surface is too low to sustain water. If you put it on the surface, it would just quickly boil away and be gone. But under the ground, where they got the weight of the rock strata on top, the pressure on that water-rich strata is so high that it can support water underground. So it's possible that there is life underground on Mars, and that's another thing which I think is pretty cool. And also, it's not just the Perseverance rover. It was also the fact that other missions, orbital missions, have actually found evidence of ancient rivers, lakes, and outflow channels, even an ocean on
Yes.
Mars. And that's kind of important because water is a key ingredient for life as we understand it. So it looks like it once floated on the surface in copious abundance. You know.
When I was
Now,
reading, Mark, they said there's only two conclusions: that it's either a result of some kind of bio process
mhm.
or other. There isn't. There was only when I was reading the conclusion on this. They are really thinking that this is possibly a biosignature.
Yeah, and again, the iron compounds again, the leopard spots, in fact, that are forming on this rock, are things that we see on Earth as microbe formed objects. So it's the best evidence so far for past evidence of life on Mars.
Hmm.
You know, so maybe NASA did find 3 billion-year-old dead Martians. Okay.
Is it possible that there could be liquid water deep within the surface of Mars?
I just mentioned that while you were looking at the PDF.
Oh, sorry. So there
No,
is. They did
un-
detect or no?
you know they did. Under the South Pole, there's a large, several kilometer long, 1 kilometer deep, I believe, briny ocean, very salty ocean, not ocean, but reservoir, we'll put it, of water, and it's potentially possible that chemosynthesis, chemical synthesis, is going on down there, just like when we look at our hydrothermal vents in the deep ocean, right? We have these hydrothermal vents that are exuding really, really hot water, and they form an oasis of life. Bacteria are coming out, and then you have in this 900-degree water, you have creatures that feed on these bacteria in the region, and then you have creatures feeding on the feeders of the bacteria, etc., and the chain goes up. How far that chain goes depends on the capabilities of the planetary ecosystem to allow for such growth of larger organisms. On Mars, we don't know how that is or where that could possibly be right now, other than underground. You know, the pressure of the atmosphere on Mars is so low
Hmm.
that um, it's effectively a vacuum for humans. You know,
Would this be a location that would be prime for a colony?
sure.
Colonization, because you have the water, you have the liquid water there to
Actually,
sustain.
there's a lot of liquid water on Mars. When the polar lander landed on Mars, and I don't remember the exact mission, but they took a photograph underneath the lander, and the lander, when it landed, its jets blew away the talcum powder light dust near the surface, exposing what looked like rock, but in fact it was water ice, hard water ice, hard as granite. And it was underneath uh, that rover, not rover, that lander. Okay, so obviously there's a lot of water ice on Mars, and all we'd have to do is harvest it in some way, right?
Yeah.
A space bulldozer, a Martian bulldozer. Let's go in and like, okay, Frank, here's this chunk, thunk. Melt it up, strain it, and give me a drink of water. It's already cold.
Are there lava tubes similar that's found on the moon? Is there anything that we could use underground that's already there, natural, that we could use as a shelter?
Yeah, there's several craters on Mars that show indications of lava tubes. You actually look down the bottom of a crater on Mars, and it looks like an opening, and then below it is a pit. So it's like there's a giant drop off into this bottom of this crater. And so you may have lava tubes of some kind that actually come through. This was a volcanic pit. So certainly the lava tubes are quite prevalent on Mars as well as the moon. It's just the moon's closer.
Right.
And so we look at the moon and there's no erosion and there's no dust that blows around to hide features. So on Mars, they're a little more difficult to detect, but we can see them at some points. But that's a great way to start a colony, is to actually create a colony subsurface where you're protected from the harsh ultraviolet rays from the sun, because that's why Mars' atmosphere is almost negligible right now, because it used to have a lot of water in its atmosphere, H2O. Okay, it had carbon dioxide, CO2. It had some methane, KCH4. And that's another indicator, by the way, interesting thing that happens on Mars. There's the methane content. So remind me in about 2 minutes to talk about that. But Mars had H2O in the atmosphere, water vapor, carbon dioxide. And what happened was, though, as the magnetic field on Mars began to slow down and wane, then the Martian magnetic field, which would normally shunt those high energy particles from the sun down around the poles and spiral them in, like on Earth, creating auroras at the North and South Pole, that went away. And so the ultraviolet radiation and the high energy particles could make it to the surface, beating down on the soils. And any H2O, water molecules, or carbon dioxide molecules in the atmosphere are going to get what's called photodisassociated. They get ripped apart by the high energy radiation. Okay. And so over time, if a cloud formed on Mars, it would go away. And why would it go away? Well, because the H2O didn't rain. It didn't cause rain if it built up to a high density like we would normally expect it to. But the H2O molecules were split apart by this radiation coming in more and more and more. So Mars accelerated to its own demise. And so since H2O made up the atmosphere would be getting thinner and thinner and thinner over billions of years until it's finally left at just this tiny, small, percentage of, volume of carbon dioxide, and leaving about 98% of the atmosphere as carbon dioxide. Now, the cool thing is that the Perseverance rover had another experiment on it that was very, very fundamental to whether we can colonize Mars. And this is one that you didn't think about, I don't think. And that's because, you think, well, how would an astronaut breathe on Mars? He'd need oxygen, right? Spock, we need oxygen.
But can't you extract that from the water?
Well, that's one oxygen atom, okay, and 2 hydrogen atoms. So you would be going through a lot of water to try and figure out how to get oxygen.
Right.
But there is another process using CO2, which is 98% of the atmosphere. You can start sucking in lots of CO2 into your device and convert for several molecules of CO2, you can make several molecules of O2, breathable oxygen.
It sounds like plants and trees.
And you end up getting some carbon monoxide as well, which we don't breathe, CO.
Right.
So, and that experiment that took place on Perseverance was wildly successful, and it was called the Mars Oxygen In Situ Experiment, MOXIE. And MOXIE demonstrated using a car battery sized, oxygen generator that it could make oxygen on the surface of Mars out of the atmosphere.
Wow.
Breathable oxygen. Now,
Wow.
Why would you do that? There's several reasons. Like, one reason is you make rocket fuel with oxygen, right? And you make oxygen that we breathe, So those are 2 major fundamental benefits of being able to make your own oxygen. So look, you can breathe on Mars. We can figure that out. Where would you live? Well, we could actually put up an inflated TAT, which I call them inflatable domes. We have them now on the space station. They did one as a test where they inflated this new module on the space station, the inflatable module, and once inflated, it's extremely difficult to make it burst. They actually put it to the burst test, and the pressure they needed to burst it from the inside was more than a human being could stand by thousands of times. So obviously, at the pressures that we need, 1 atmosphere, it's in hog heaven. It's not going to ever have a problem. So if the inflated TAT was on Mars, a large one, small one, connected to each other, well, then you actually can create oxygen using the MOXIE units. Just make bigger ones. If you had a MOXIE unit the size of a golf cart, okay, then you can make more oxygen than you would need for that inflated tat. Okay. And so you can actually send a robotic mission up there to inflate the habitable dome. And then the MOXIE unit could be used to then fill that dome with oxygen. And then with that, you can also have a robot inside that oxygenated dome do something else, and that is study the viability of growing plants using the Martian soil, which is very sterile. But with the addition of some additional nutrients, some nitrogen and so forth, and some fertilizers, maybe the Martian soil would be viable to grow some plants. And if that's the case, this could all be started robotically with cameras transmitting progress. I can just see the first time they see a little, bean cotyledon form in the ground. They go, yeah, I can see everybody in NASA, congratulating themselves. I can see that happening because it'd be a robotic mission. Right. And then only after that would we end up going to Mars, where we know we actually have the ability to survive. We'd have water, we'd have oxygen, 2 biggies, and then we can actually make beans and potatoes and other plant stuff that we could use to eat. Corn would be a big one to grow on Mars. But again, you're going to need special lighting, and the lighting has to come from Earth because the light of the sun on Mars is not going to be strong enough. Effectively, remember when the dinosaurs died out because the plants there was a pall of dust in the air from the asteroid. Yep. Yeah. Well, when that hit, that destroyed, all the plants because the sunlight was dimmed enough so the plants died. Well, the distant sun at almost 2 astronomical units away, twice the distance that we are from the sun at Mars, would be so dim that it would be really, really hard to actually have
as a power source.
To have the sun be the supplier of sunlight to make plants grow.
Right.
Because we'd have to let that sun get in without letting the ultraviolet light get in. Okay. Now, I do want to comment on something that Michael's Asylum mentioned, which is, of course, true. We can't breathe pure O2. Well, we can, but it's going to burn our lungs. We'd need the nitrogen. That is correct. So we would need to have a way to have nitrogen, which is why I mentioned the nitrogen fertilizers in the soil. Okay, because with that, we would have to have a way to have nitrogen as well mixed into our air that we would breathe. Now, the astronauts, prior to the later Apollo missions, and we did go to the moon, I don't want to hear it, the astronauts breathed pure oxygen in the Apollo capsules prior to launch. And that's the reason that they died. The Apollo 1 astronauts died. Grissom, Chaffee, and White on the launch pad, because oxygen is also something very bad if you have a fire nearby, because it's the perfect catalyst to keep a fire going more and more and more. All right. So we'd have to be very careful about how we develop the oxygen and what we're going to mix it with. That's the way it's going to be. Now, they might try something else. They might try some exotic mixtures.
So, the astronauts on Mars might talk like this because they would be breathing some helium or something to go with the oxygen.
I mean, they might have a special mixture, heliox or whatever they are. And so they would end up having, high-pitched voices. It's like,
hi, phone call from Mars. Hi, guys.
Dad, you sound different.
Oh, it's okay.
It would sound kind of weird. Yeah, we're the munchkins of Mars. So I think that's hilarious. So obviously that kind of thing is going to be happening as well. Kathy says Marvin the Martian. Abby Love says we should build a space station for humanity versus trying to develop Mars. What are your thoughts? Very good question, Laura. Laura Newbert is a very smart lady. Met her at Devil's Tower UFO Rendezvous, where we had 2 years worth of UFO conferences there. Well, again, the question, the question is, she meant Abby Low. I know that.
Eventually, we have to go off world as a civilization anyway.
Yeah, I mean, currently we have space stations. Now we have a space station, right? Well, we're not even unified. The Chinese have their own.
Yep.
The Russians had their own before
They're
they joined
planning
us.
another one. They're planning another one.
Yeah. Um,
30s.
yeah. Now our space station is showing its age, and it's going to be possibly 2028 when it's deorbited.
Yep.
I hope that show goes over us. I'd love to see that.
Yep.
That's going to be a massive sparklers landing.
Gosh.
Yeah, just a
Probably
small
go
one.
to the Pacific, I would think.
Well, they're gonna drop it into what's called the satellite graveyard, which is in the Indian Ocean. So unfortunately,
okay.
Well, there's one in the Pacific too, but the Indian Ocean is somewhere where they're probably going to go. I think it's the Pacific. Maybe it's the Southern Atlantic. I'm not sure. I have to check. There's 2 satellite graveyards. I'm sure our very smart listeners will let us know. Yeah, but building space station to preserve humanity versus trying to develop Mars is interesting. Why, again, it comes down to this. Why do we feel compelled to stand on another planet versus just be off-world? There's a few things. First of all, if we go to another planet like Mars, okay, one of the problems we're going to have is that the gravity is much less than on Earth. However, it's not zero gravity. All right, we're going to have some gravity, and with additions in our spacesuits or whatever, our bodies could still get the same kind of exercise that it would get if we were on Earth. And so you'd feel like you're walking on Earth, but you'd be walking in a much lower gravitational, field. So that said, and there's caveats all throughout that whole concept, but the bottom line is that as long as your muscles are working hard enough, you won't atrophy. Your muscles won't go to nothing. Astronauts on the space station lose a significant percentage of their mass and their muscle mass when they're up there too long. Yeah. And when they come back, you'll notice that the first thing that happens is when they take them out of the Soyuz capsule, they carry them out of the capsule because they've been up there for like 300 days, and they sit them in a chair. They can't walk. They can't walk when they get back. They have to learn how to do that again, slower. And so if we go to a planet, even the moon with 1/6 gravity, it's not going to be as punishing on us physically as it is to be in orbit. Now, one thing that's interesting about orbit, okay, and this goes to Einstein, is that if you're in orbit, you age slower. Okay, you are physically aging slower when you go into orbit. The faster you move, the slower you age. So if you're close to the Earth, like the space station is 200 miles up, well, you're gonna slow down. Now it's a very, very small fraction of a second, per second or per minute, but it's still enough to add up if you're up there long term. So I guess if you wanna live forever, as they say in Starship Troopers, you want to live forever? Well, the bottom line is just go into a fast orbit.
Plus, the ideal situation would be, when we have that technology, many years from now, it would be an exoplanet. Obviously, that would be like the optimal situation. So,
yeah.
About taking those steps, baby steps. It's really all about baby steps.
That's right.
It's just a matter of time when the Earth's surface becomes uninhabitable. We're going to have to go underground or off-world eventually because...
Yeah. And Marvin the Martian will be happy at that point. He says, I'm going to blow up the Earth. What you doing that for, Doc? It obstructs my view of Venus. Oh my gosh. And us Martians get very angry indeed.
You asked me to remind you were going to mention something to do with methane before we wrap up. We got about 5 minutes.
Yeah. Mars showed a really interesting bloom of methane, which couldn't be easily explained and not really explained to this day. During the Martian summer, they actually noticed a gigantic bloom of methane across a large swath of the planet. Methane can be generated by volcanic eruptions, but Mars is tectonically inactive right now. Methane can also be produced by frozen methane underground being liberated through heating in the summer. Those are called clathrates, or methane hydrates. We have them in the bottom of the ocean. And if it gets warm enough, they could come boiling up to the surface. And methane, of course, is flammable. There is a story about a tidal wave, tsunami, that came on shore, and ahead of it was a massive flaming trough of water, because they thought maybe the tsunami was created by a methane hydrate field that burst open because of changes in pressure or an earthquake.
Wow.
And that disturbance came to the surface. There must have been a lightning storm, ignited the methane, and for a period of time, you had this rolling wall of fire coming in so that you get burned while you drown.
Oh, why?
That's, yeah. So, but on Mars, but the methane comes from organic processes. That's the thing. Okay. Yes, it can be generated by volcanoes and so forth, but a substantial amount of it in a concentrated location could also be due to biological processes. Cows on Mars? No, but still. And it's CH4, carbon, hydrogen, 4 hydrogens. Okay. And it's a stable molecule. And so, interesting thing about methane is that we saw this bloom on Mars one Martian summer, and the next Martian summer it wasn't there. So what happened? Were those microbes that just sort of burst to life momentarily? If so, what caused that? Where'd they come from? Underground, likely. Could it have been an impact that sparked the chain reaction? Yeah, maybe, but we don't know. So Mars has lots of mysteries we don't understand, without a doubt. And methane is a key molecule in the building block of life. So I think it's really important to figure that stuff out. So
Well, we got a couple of minutes, Mark. When are you planning to stream?
Well, I was looking at my Sonoran scope here. The Sonoran scope is not up right now, and it's cloudy in Benson, so I can't do that tonight. Yeah, it's actually quite cloudy in Benson. A storm came through, so I can't do either telescope tonight. But you know what? It's okay. I literally made myself sick because I'm not sick now, but the other night I started doing part 1, part 2, and part 3 of the Summer Milky Way tour. And we started from Sagittarius, went all the way up into Cygnus, and all the way up into the northern reaches of the sky over 3 nights. And each night I started at 11 p.m. and went till like 2 a.m. Okay, and I still got up at like 8 a.m., 9 a.m. So 3 nights of that, and the third day I was going, la, 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 la. And it's like on Gilligan's Island when they have that music where they're not drunk, but they've ate fruit that's bad. Like my head was like all over the place, But so I can't really, I really don't know,
SkyTourLive.org or SkyTourLive.com. Make sure to check it out. There's a lot of great stuff on that website.
Yeah, we actually, that's fantastic. And, don't be afraid to go visit our SkyTour portal, which is Bill just told you, SkyTourLive.org. Love having you. And, if you want to talk to me directly, you can contact me right there. Contact SkyTour@gmail.com. I know he does.
Also, he's on TikTok as well.
Yes, please join me on TikTok as well and follow me on TikTok. I want to start streaming on TikTok as well, and I got to talk to you about that because I had a menu pick on my TikTok that says "Go Live," but
I will show you
because I don't know if that's actually really go live. Doesn't seem like I couldn't find the stream key.
Yeah, no, I'll show you how to do it.
All right,
we'll talk about that off here. But always a pleasure to be part of this show with you. Hopefully Tara will be back for the next show. I know it was last minute.
I didn't give her any notice because I wasn't sure I was gonna be able to do it, but I'm very happy I did. I also want to make a shout out to Asterion Foundation, who has give us a small grant to get some equipment for the Benson telescope. And we got part of that equipment now, and we're going to be getting more here in a little while. We're going to put a spectrograph in there.
Check
And
out the merch too at the website.
Oh yeah, that's right. We do have go
Cool
to the
stuff.
website. Yeah, you want it on socks? You want it on boxer shorts? We got it. Bathing suits. You want pictures on the glass? You want pictures on canvas? Pictures on metal? Got that. It's just amazing. And here's the thing. I get nothing for this. I'm not taking a paycheck for anything I do. Okay, with Sky Tour live stream. It's because I just decided I was going to be an outreach astronomer, and I figured I'll just let the environment take care of me.
This is truly a public service program.
It really is.
It's an
free education in astronomy.
Absolutely. I always say that. And on TikTok, it's Sky Tour live stream, all one word.
That's correct, yeah.
So make sure to follow. This way he can start streaming there as well.
Yeah.
Mark,
we're on YouTube.
Well, seconds left.
Okay, we're on YouTube, Rumble, Twitch, Trovo, Kick, soon to be TikTok, and Facebook I can't stream on anymore because my profile was stolen.
Oh gosh, yeah.
And I still can't do any live streaming on it for some reason. Doesn't matter. Okay. Anyway.
And so all of you for being here tonight in chat and making, helping with the interactiveness with the questions.
Yeah, fantastic folks.
Great to have you all here during the show. Looking forward to hopefully the next one next week or seeing how schedules work out. But thank you all for being here tonight.
Thank you,
those
Toner.
that are listening as well. So Mark, you can close it out for us.
Okay. Well, guys, thank you for coming, and I'll keep you posted on the status. Look for any status up in the Sky Tour live stream group chat. You can join; it's all free, and Sky Tour is free, by the way. You don't have to pay us a dime. If you want to, that'll help us, but you don't have to. And the pictures, we give all the pictures away that we take for free, just so you know. If you want to buy them special, you can get it from the store on different items, water bottles and so forth, etc. But we actually do this all for free. So think about supporting us. We'd really love it. Thank you. You guys have a good night, and we'll see you on the next Sky Tour live stream and Sky Tour Radio. Right, Bill? Yeah.
Yes. Have a good night, everybody.